Conventional gas-fired forced air heating system flame ignition. In this presentation, we're going to be looking at flame ignition in the form of a standing pilot, what that means. We're going to look at flame proving. We're going to look at pilot safety valves, combination gas valves, and finally, we're going to finish with the full operation of a heating system. A basic standing pilot burner. This is an example of a basic standing pilot burner, which means that a pilot light or a pilot flame, a small flame, burns constantly. The way in which we set up this system initially is we need to take a outside form of ignition and light the gas that's coming out of that very small orifice. Once we do, that flame remains lit constantly. The flame should not go out for any reason, and if it did, it would be bad. So what the purpose of the standing pilot is to ignite the main burner gas when the thermostat closes and the main gas valve mechanically opens. The flame ignites and the pilot burner continues to burn. And when the thermostat opens, the main gas valve then turns off and closes mechanically, but the pilot burner continues to burn. Now, the problem with a basic standing pilot burner is that if that flame were to get snuffed out, over time, gas, whatever the type of gas is that's being utilized, would seep into the area where the furnace or the heating system is located. And because of this, it's not a very safe system. So in addition to a standard pilot burner, there must be some other form of control. And that form of control comes in the way of flame proving. Flame proving is a mechanism that all heating systems have. They have a way of automatically shutting off the gas flow if all flames are extinguished. Now, this is accomplished through the system proving that a flame is present. And so what the system needs to do is prove that a pilot flame is always there. And if the pilot flame is not there, then we should close the gas and have no possibility for gas to flow out through the pilot burner. The way we're going to do this is we're going to use a thermocouple, and connected to the thermocouple, we are going to have a power unit. Now remember, a thermocouple is an object that creates 26 to 32 millivolts DC. And at the end here, this junction, it has a threaded connection typically, and the tip is the positive and the shroud would be the negative side. This is not a typical electrical connection, but it's one intended for a specific purpose. What this is capable of powering is a very small electromagnet called the power unit. And this power unit can be used to then control many different things. This example down here shows a power unit controlling a normally open contact. Now, there are two different ways that a thermocouple in flame proving can be used with this electromagnetic coil. The first way, as we just said, was to operate electrical contacts. The second way it can be used to control the system is to hold a pilot safety valve in the open position, which we'll talk about in a few moments. This is what the electrical contacts could look like. The power unit is an electromagnet. It's powered by the thermocouple. And remember, the thermocouple generates electricity when it's exposed to a flame. And that's why this thermocouple is positioned right beside the standing pilot burner. If there is flame coming from the standing pilot burner, the thermocouple will be hot and it will generate a voltage which will energize the electromagnet, which will then cause a contact to go to the closed position when energized. The way that this would then be used when connected fully into the system is shown below. We can see that this pilot safety switch is located in series with the thermostat, and the power unit, energized, will close the contact. When the contact is closed, that means that the thermostat has a full closed circuit in order to operate the main gas valve. Now, if the thermocouple were to cool because for some reason this small flame has been snuffed out, the power unit would de-energize slowly and the contact would go open. Now, what this would mean is that the thermostat would not be able to operate the large main gas valve. There would be an open circuit here, and the main gas valve would be inoperable. However, there would still be a small amount of gas that would leak through this pilot assembly. And so although this is slightly safer than other types of control, there is a much better system available to us. And that's in the form of a pilot safety valve. A pilot safety valve is using that electromagnet that is powered by the thermocouple to simply hold a small gas valve in the mechanical open position. If the electromagnet were to be de-energized, the valve will close. Now, why is there a manual reset button? We'll take a look at that in a moment. So this is the entire system that we would typically see, as now we have a pilot safety valve. Now, if we look at the flow of gas, it's before the T, which allows for the pilot burner to receive its own small volume of gas, and it's also before the main gas valve. This means that if the thermocouple were to cool, the pilot safety valve would then mechanically close and prevent zero gas from flowing anywhere out of the system, no matter if the thermostat called for heat or not. In most modern applications, this design has been compressed into a combination gas valve, where the pilot safety valve is part of the main gas valve, and there are two separate gas valves in this one object. It looks like this typically. We can see a threaded connection for the thermocouple. We see electrical connections on the main gas valve that the thermostat would be controlling. We also have a manual on, off, and pilot setting. If we were to crack this thing open, we can see that there are indeed two separate electromagnets. One of them is the pilot safety coil, and that would be controlled or powered by the thermocouple. The other one is the main gas valve coil, and of course this is controlled by the thermostat. If we were to look at the entire system with the flow of gas and the operation of the thermostat, it would look somewhat like this. What we have is a main gas rigid steel pipe that's bringing natural gas to the main gas valve. We then also have a thermocouple connection. The thermocouple is threaded into the main gas valve, into the power unit, and it will energize this small electromagnet. The thermocouple is the black line along the bottom of the screen, which then ends here beside the pilot burner. The pilot burner is supplied gas through this small line all the way through to this chamber. When we look at the flow of gas, the gas is going to have to first enter this chamber, and then when this valve is opened, it will seep into this main chamber here where we see a green regulator. The green regulator is simply something that regulates how much volume of gas is flowing through to the burner and not something that electricians typically are involved with. Over here is the main gas valve. It's much larger, and this one is energized and drawn down when the thermostat, which is located here, calls for heat in the room. Now, there's a few other additional items that we see in the electrical circuit, which is the high limit, and we're not going to focus on that too much here. And then we also have a transformer and an electrical disconnect. What we more want to follow is the sequence of operation that takes place. All right, so first thing we need to do is allow gas to flow into the initial chamber. And so we have a shutoff valve here. We're going to open the shutoff valve. And what we see is that there is now gas that has filled this initial chamber. Now, the thermocouple needs to be hot in order to allow for this valve to be in the down position. And if we want gas to flow through to the pilot burner, we need to somehow allow it out of this small chamber. And this is the reason for the manual push reset button. The manual button is used with a finger to depress and allow gas into the main chamber. So what we're going to do is press it down. And in doing that, we've allowed gas into this main chamber as well as this small line that supplies the pilot burner. At this point, while we're holding it down, we're going to take a match and we're going to light the pilot burner. Now that we've lit the pilot burner, we still have our finger pressing down on this valve. Eventually, the thermocouple is going to reach such a temperature that it creates enough voltage that the electromagnet will hold this valve in the down position or open. I can now release my finger from that manual push, and the pilot burner should stay alit. And again, the reason for that is because the voltage generated by the thermocouple is enough to simply hold the plunger in, not enough to draw it down from its upward position. Okay, so now what we're going to do is energize the electrical circuit here. And then again, we're going to focus on the thermostat, which is on the right-hand side. So let's close the disconnect. And now let's call for heat by saying the thermostat has called for heat in that the room is too cold. So as the heat drops in the room, this will contact the second side of the thermostat terminal, and what will happen is the main gas valve electromagnet will energize. When it does this, gas flows out from the main chamber to the main burner assembly, which is allowing then combustion gas to go up into the heat exchanger, and it is lit automatically simply by a flame that is always standing off to the side. When we finally do reach the temperature that the room is required to attain, the thermostat will open. And when it does, it de-energizes the main gas valve. The main gas valve closes, the gas stops flowing through to the main burner, and the flame extinguishes. Notice that the pilot flame continues to burn consistently throughout this operation. So again, what we have is two separate electromagnets that control gas valves. One of them is the main gas valve, controlled by the thermostat. The other one is a small pilot safety valve, controlled by the thermocouple. Finally, there is a way that we could test the voltage of a thermocouple, and usually that's called an open circuit test. Open circuit meaning the thermocouple is not driving or supplying any electrical load. In order to do this, you need an ancient DC millivoltmeter from the 1930s that's analog. No, I'm totally kidding. I don't know why this picture has an exceedingly old voltmeter. It doesn't need to be from the 1930s. All you need to ensure is that one of your probes contacts the sheath, and one of the contacts, or one of the probes contacts the center tip of that thermocouple cold junction. And when heated, you need to see around 30 millivolts DC. Finally, why would you want to do that? Well, if you're not getting 30 millivolts DC, it's probably one of two different situations. One could be that the thermocouple is bad and it needs to be replaced. The second could simply be the amount of heat applied to the thermocouple. If the pilot flame is too small, it won't have enough heat to heat up the thermocouple to a point where we get the rated 30 millivolt DC value. Another option could possibly be that the thermocouple itself has been bent away from the pilot flame and is not directly in the flame itself, thereby reducing the heat exposed to it. Either way, it could possibly be that the pilot flame needs to be adjusted. And to do this, a small screwdriver is used to adjust what's called a needle valve. The needle valve simply constricts the flow of gas to the pilot flame, and it's a very simple adjustment that can be done by an electrician.